Okay, welcome back in our deep learning and edge computing course. This is a part 2 of DNN. Okay, so in part 1, we mentioned about forward propagation. And if you remember, we have a preset weight and a bias, right? And we put all the input value into the forward propagation process layer by layer. Then we get the output. Okay, so here maybe the output we have two values, y1 and y2. Okay, so so if you remember, what we did is we already have the weight. Okay, but actually the weight we need to use some way to get the right way, right? So that's called backward propagation. We need to use certain way, a kind of way to find out the right way. Okay, so the mechanism here is called, later we will introduce, called a gradient descent. Okay, gradient descent. We use this way to find out the weight. And beginning with loss function, okay, a loss function. So later we will use derivation, okay, technique to find out how to minimize loss. So the first thing is we need to define a loss functions. There are different kind of loss function. Because the example right now we present here is more like a regression example. Okay, so the output of yi, say maybe 3 and 4. Okay, then we have a ground truth. That's the label value we put in the supervised data set, right? So that may be 5 MA. Then we have the error. So the loss function we used in regression a lot is called MSE, mean square error. Okay, the calculation is quite simple. Is that we summation, okay, we summation all the difference between the ground truth, okay, and output value, okay, and use the square value, okay, and divide by 2n. Okay, that's the loss function. Okay, we use a lot. Okay, once we define the loss function, then we can apply the gradient descent. Okay, gradient descent. So we talk about the backward propagation. Actually, we use a gradient descent mechanism, okay, to update the weight. The gradient descent is based on a derivative of the arrow function regarding the weight w. Okay, so it's if you study the derivative, you may know that actually this is we find the changing rate, okay, of w that will have the output consequence for the arrow function e. Okay, so here is the gradient descent equation we used. Is we will update the old weight. Actually, in the beginning phase, we will randomly set up the weight value, okay, in the weight matrix we mentioned in the last section. Okay, then when we have the after chaining, we may have the ground truth, okay, and the inferencing value, and we will, we will find out the value for the loss function. Okay, then we can just use the derivative of the loss function. Okay, which is we find the weight changing. Okay, that will affect the loss function. Okay, so we update the weight. So every time we have every time in the chaining process we have a new loss function value. Okay, then we will update it. Okay, that is based on we update the old weight. Okay, and minus a little on the change. Okay, of the output value. Okay, so in the example we can see this figures. Okay, you see this is the weight, and this is loss function. Okay, so every time we update the weight, okay, if we update the weight based on the derivative of the loss function, then we will follow the curve, okay, because that's a changing rate, right? So we update the weight, follow the curve, then little by little, we might find the minimal value, okay, for the loss function. Okay, so that's the principle. Every time we have the old weight and we update, okay, and we got the new one. And then we have the new one set up in the weight matrix, okay? Then we do the inferencing again, okay? Then we have the new loss function output. Then we, again, it still has arrows, okay? It's still not approach the minimal. So we update the weight again, because every time we update, we use the derivative of the loss function E regarding weight. So we will remain on this curve until we find out the minimal value. So the interesting thing is how faster we update the weight. Okay, how faster we update the weight is using the parameter called learning rate. If we set the learning rate larger, then we update the weight, maybe have a big jump. If we have a big jump, we might miss the minimal value. Okay, so normally we use a very small value to do this gradient descent. Okay, that's normally maybe 0.0001. So we update 0 by 0. Okay, but there are some cases. We cannot always use a little value, because sometimes the curve looks different way. Sometimes we have a curve that is so complex, it's not very easy to find the minimal value. Okay, so there will be time we might also use a larger learning rate. It's based on the condition we process in the learning. Okay, so that's optimized section we might talk about in this course. Okay, but you can first understand that we should set up a very small learning rate to update the weight little by little. So that's called gradient descent. So if you have you already have the concept, so next we will have a concrete example for you to realize how do we do the chaining, which is how do we update the weight so we approach the minimal error for the loss function. Okay? Okay, here we will use a real example to illustrate the idea of the gradient descent. Okay, so we use a very simple neural network. Okay, it's provided by Google. Okay, and later in this Google website, you can see the whole process. The neural network here is only one input and one output. Okay, so neural network can be one input, one output, no problem. Okay, because if that is for a kind of prediction, okay, only output a single value. For example, age. For example, the score you will win something. Okay, so but it's not happen a lot. But it's just use a simple case help you to realize the mechanism of forward propagation and the relation between forward propagation and backward propagation. Okay, so we will jump into this website. Okay, so here we see this very simple neural network. Okay, we have input, only one input. Okay, and here we have hidden layer. We have two layers. Okay, and we have only one node in the output layer. Okay, so as we mentioned earlier, so there will be weight, okay, to set up in this neural network. Okay, and so every input will certainly by multiply a weight to affect, okay, the next layer. Okay, so here we for example, we see the node 4. So we have W24, that's for node 2, and W34, that's for node 3. Okay, so that's a case that you memorize how it works in the basic neural network. And another thing in the neural network, every node if you remember, we have a value, right? In the original last section, we use z value. I'm sorry, the Google used a different. It's just always use the x. Okay, so you can transfer the x is the z value we mentioned in the slide, and we will put the value into an activation function. Okay, to get the final output of a node. Okay, so the activation function here, we use sigmoid. Remember, we mentioned several activation functions, just like sigmoid, ReLU, and softmax. So here we use sigmoid activation function. Okay, and in the end, if we need to calculate the gradient descent, so we need a arrow function. So here the arrow function, we also use the MSE arrow function, okay, which is calculated by this equation. So every output, okay, we will find the ground truth and calculate the loss function. Okay, another name is also arrow function. Okay, so that's where that we start the forward propagation. Okay, so through this stage by stage illustration, you may realize the relation in between forward propagation and backward propagation. Okay, so so this beginning with input, right? So we go by very slow. Okay, so we'll start to do the forward propagation, which, if you remember, that is this equation, we will multiply the output of the previous layer, okay, with the weight, okay, and summation and plus a bias. Okay, so this is forward propagation. Then we will the y1, okay, will also has impact to the x3. Okay, then we continuously this forward propagation procedure, okay, which is this equation, right? Okay, we do it just layer by layer. Okay, layer by layer. So this in this layer, you may see the x4 we just mentioned. It will has impact from the two previous layer output, which will be y2 and y3, right? So we just follow up this forward propagation. Next layer, we have y4, y5, and here we go to the final layer. So the x6 is the value which calculate the previous layers output and the weight. Okay, and then in the end we put into the final activation function. Okay, so then we will get the arrow. Okay, because once we get the output, because it is a supervised learning, then we can compare the ground truth. Okay, then we can calculate the loss function. Okay, and just like we mentioned in the slide, then we will do the gradient descent calculation. So in this figure, I think it's more clear. We have a lot of weight, right? We have a lot of weight we need to update. So in this gradient descent algorithm, you see that it's W ij, okay? That means for every input to the for every input of the layer, okay, we need to update the weight binding with the previous layer's output. Okay, so we need to update one by one until we update all the weight. Okay, and the weight will update based on what? Based on the learning rate. Okay, if you remember the figure, we update little by little. Okay, and when we update, we need to follow the rate, right? The rate is the derivative of E regarding weight. So that's why when we update the weight, we can still, stay on the curve, right? Okay, based on the rate. Okay, so this is graded descent. Okay, so but to calculate, to calculate the every weight, okay, we need to find out a very important part of this equation, which is that weight's derivative, okay, which is the arrow function, okay, which we need to find out how the weight, the ij, will impact the final arrow function, right? So here we got a problem, right? Here we got a problem. We have the arrow function E here, right? We need to find how this weight change will affect this, okay? But actually, the weight will have impact to x6, and x6 by the active function will impact y output. So it has a chain, okay? It's a chain action, right? Actually, the chain starts from the very beginning of this weight. So this weight have impact of this, and this have impact of this, and have the impact of this. So it's a chain action. So when we need to find out the dE over dWij, that's a thing we cannot do, use forward way. We will need a backward way. Okay, what's that? What's the meaning of that? You can see the next slide. If we want to find out the derivative of dE over dW, then by chain dual, we need to find out the dE over dx6 and dE over dy6. Okay, then we can find out this value. Okay, and when we need to find out this value, okay, we need to find out dE over dx4 and dE over dy4. So this will be a totally inverse action, okay, from the opposite direction. So that's called backward propagation, because we need to find out this value, this value, this value, this value, this value. So the direction will totally be inversed, okay, upside down. Okay, so the detailed calculation later we may mention a little in the slide, but you can see the progress is just like what I mentioned. It's followed a totally inverse direction. That's called backward propagation. We find out these, we find out these, we find out these, then we can calculate this. Okay. The point is we need to calculate all the dE over dWij. Okay, so we need to process from the output layer, and we move back. Okay, previous layer, we need to find out that layer's dE over dWij. Okay, and we go to previous layer to find out this layer's dE over dWij. And when we need to calculate this, we need to first calculate the upper layer's derivative value. Okay, so if we can find every value, we will come to the end. Okay, so that's the actually process of the backward propagation. So we go to the slide, see some derivative equation illustration, but it will not be the main goal of this course. So I will just mention a little, okay, for your reference, okay, because this is based on derivative, okay. So we need to find out the derivative, okay. So the derivative, again, we provide the gradient descent function here again, okay. So we will discuss how to find out each value. Okay, let's go back to the slide, and first let's recall in the website. Okay, this is the neural network we just mentioned, right? We have the activation functions, and we have the loss function, which is arrow function, and we have processed all the forward propagation based on the equation for weight and previous layer's output. Okay, then in the end, we have the value, okay, from the very last layer's output, right? So so here we already have the value of the output. We can calculate the loss function, okay, and that's the forward propagation. And then the next step, we need to do the gradient descent mechanism, and we mentioned the gradient descent mechanism is we update every Wij based on the derivative of E regarding Wij and multiply learning rate, okay? And so how do we update the weight we just mentioned? Is based on derivative, okay? So later, I think we will spend some time to have some explanation on the derivative. But before that, that's because the main goal is not the derivative, right? The main goal is the learning. So let's first have a big picture on how the learning works, okay? So after you know some kinds of derivative, we may get the d over dw, okay? So we will update. But when we update, we have two directions, okay? Because the d over dw is a slope, right? So if the slope is greater than 0, that means we are on the right side, right? Okay, so we will update it, okay, and update. And once we find the d over dw is little than 0, then we are on the left side, okay? So we will increase the weight. So the whole process is we might decrease the weight, okay? So this curve goes this way. And once we find we are on the other side, we will increase the weight until we find this minimal value of the loss function, okay? So the whole process we can just first have a summarize here, okay? Again, it's for a big picture, let you to understand how it works if you don't have interest on the derivative. Of course, later we will introduce some, okay? So the whole picture is, you see this figure again, we need to update all the weight, okay? So here we have a note, update all Wij by increase or decrease value based on the learning rate, okay? And based on it's multiply the derivative of E with respect to the weight, okay? So so I give you an example here, okay? If the originally W12 equal to 1, and the learning rate alpha equal to 0.001, and at that time, the d over d W12 is 2, then we just apply this equation to update W12, which will be 1, okay, minus, okay, 0.002. Okay, so we just update a little. So this will become a new weight. So based on the derivative we got, we will update every weight. Based on the learning rate. Okay, so once we update all the weight, then we will put another input data, okay, to do the forward propagation. And eventually we will get the output. And we might also see the loose value again. So we do this calculate again. So that's the relation in between the forward propagation and backward propagation during the learning cycle. Okay, so in the learning cycle, we still have to do the forward propagation because we need to get the new arrow value, so we can update the weight. Okay, so that's the whole process. And one question is, when will the process stop? That's a very important thing, right? We don't want to change until we need to find out the goal. So the goal is we cannot minimize the error anymore, so we stop. Okay, maybe that's already good enough, or maybe the data set does not make sense. We may update the data set. So that's that will be the other topic of how to optimize the chaining. Okay, but here you may know that we will stop the process where we can't update anymore because we already all the error value remain the same. Even we chain, the error value remain the same. At that time, we will stop the chaining. Okay. And so here we have another section just for you if you have interest on how we do the derivative calculation. So first, I want to introduce a very basic idea on calculus. I think we might have this background. So just mention a little on the calculus. Okay. So the calculus is, especially for derivatives, is all about we find the rate. Okay, we find the rate when we change that input value by the rate, how it will impact the output value. So that's that's a core concept for derivative. So here we provide an example here. So if x equals to x squared, okay, square of x, then the derivative of that f function will be 2x, right? This is the basic of the derivative. And what's the meaning of that? We provide example here, okay? So if we have a very, very small value called epsilon, right? And we update it very, very small value. We just increase it by 0.001, okay? Then by the equation, okay, we may see the final output value become 100, okay, 0.002, okay? And if you see the difference between the output value and the original value, you might find our update rate is just approximately the 2x because it's 2 times 0.001. So if epsilon becomes 0.002, we do this again, we can find it's become 100.004. So the rate is also remain 2x. So the derivative, the core concept is to find out the changing rate, okay? And so that's very important. So that's why we need to do the derivative for dE over dW, because we need to find out how we change the W will, impact the arrow, okay? So to calculate the different dE over dW, we may first have some make some derivative for the some given function we already knew. For example, so this is a loose function, right? That's a e. So we first need to find the derivative of the loose function. Okay, so based on the derivative principle, we can get this is the derivative of the loose function. And this is a sigmoid function, right? In this example, we use sigmoid function. So this is a sigmoid function definition, right? So by derivative principle, so after a few step calculation, the derivative of a sigmoid become the fx multiply 1 minus fx, okay? And for any w multiply x, okay? And that's we see a lot in the whole neural network, right? W multiply x, okay? So the derivative of wx is w, okay? So this is something we can calculate first, okay? Because that's some given function, okay, and given operation we already knew. So based on this thing, then we can start to do the derivative calculation, okay? So here we just to give you some of the examples. So based on the first some of the example calculation, you apply the same principle. After a while, you can calculate all the dE over dW. Okay, so that starts from this backward propagation from the first node. Okay, from the first node. Okay, the first thing, okay, is start from the loose function E, right? Okay, so that's the equation of the loose function, right? Then the derivative of dE over dy, right? The y, because the y, minus the target, right? And we use this loose function to calculate the E, so it's very easy to find the derivative of the d over dy. So just based on the derivative principle. Okay, so here is the d over dy. Okay, so we already have this. Then we need to calculate dE over dx, right? And the d over dx by chain rule. Okay, by chain rule. Okay, because the x may impact y, right? And finally the y impact e. Okay, so this is just a chain rule. Okay, so the d over dx will be dE over dy multiply dy over dx, right? So and because we already have the d over dy, all right. Right now we need to calculate the dy over dx, and how the x will impact the y. Basically, we just mentioned it's a sigmoid function. Okay, so we already have the derivative of a sigmoid function, which is fx multiply 1 minus fx. Okay, so here we also get the dfx, which is dy over dx. So calculate dE over dx by the chain rule. We already have these two equations. Okay, so here we got the d over dy. Okay, so we have the d over dy. Again, this is dy6 because it's the final layer is the naming 6, and we already have the d over dx6. Then, based on the two calculated value, we may start to move forward to get the dE over dW. Okay, so that's the starting point of the backward propagation. In the last slide, we already have the calculated value of d over dy6 and d over dx6. Okay, so by the backward propagation, then we can get the d over dw. Okay, so we can see that again we have the loose function e, and we have the d over dy based on the derivative of this loose function. Okay, then we by the chain rule, okay, we can get the d e over dx4. Okay, so we already get the value here. Okay, so next we can forward to get the dE over dW46. Okay, and also, so it's all about chain rule. We also thanks for chain rule. So based on the chain rule, we know that the W has impact to X, the X has impact to E. So we can use the chain rule to get actually it's dE over dx6 multiply dx6 over dW46. We can swap the two factor. So on the left side, the d over dx6, you can see in the equation we already have that, right? So we already have this, which is equal to what we got, right? So the final thing is we calculate the dx6 over dW46. And by the forward propagation formula, we know that the x6 equal to the y4 multiply W46 plus the y5 multiply W56. Okay, so by partial derivative, because it's only concerns the W46. Okay, so this will be the left half will be 0, so the output will be y4. Okay, so we put the y4 into this equation and multiply what we already got. So this is the way we get the dE over dW46. Okay, so here we can also have derivation for all the calculation. We can say that any d over dWij is equal to the yj multiply d over dxj. Okay, so that's a quick illustration on the backward propagation, right? We get one by one by derivative. Okay, so we follow the principles, and we can calculate all the value. Okay, there will be certain value that the input will impact to the next two output. Okay, so we need to apply that kind of chain rule. Okay, so it's for example for y2, because it may impact to w x4 and x5. So eventually by derivative, it will be this equation. Okay, so just to use all the procedures we can apply on the other path. Okay, the left path. Okay, and also get the other value. Okay, so we repeat this. Then we can continue to complete all the calculation of dE over dWij. Okay, once we have this value, then go back to the gradient descent. Once we have all the dE over dWij, and we choose a learning rate, then every time we do the forward propagation in the chaining, we will get the error value, so we can update the new weight. So if we have enough data, we can update it after a lot of chaining. Hopefully, eventually find the minimal value of a loose function, and at that time, all the weight in this neural networks are optimized. Okay, so that's we call a model. So the model of a neural network is nothing but nothing but a chain, a weight. Of course, we also need to apply the same principles, the same procedures for the bias value as well. So we just mentioned about the weight, but you can just use the analogy, use the same mechanism. We will also update the bias. So once we have optimized the weight, all the metrics, and the bias, all the metrics, then it's called a chain model. Then we can remember in the introduction section when we talk about the purpose of this course is to combine the neural network and edge computing. Once we have the chain model, optimize the weight and bias, we can put that model into edge devices, start to do the inferencing. Of course, we may still find something we need to update, so that will become the next chaining phase. Okay, so it's just called ML ops for this total edge computing and neural network engineering. Okay, but when we talk about chaining, how did you evaluate it's good or it's not good? We need certain kind of metrics to evaluate, right? So next section, we will talk about how to evaluate the chain model. What are the performance indexes?